So when you are given a function to graph, when graphing, what kind of things should you notice? What kind of things should you think about? Right. First, you try to find the domain of the function, because if the function is not defined at certain parts, like the negative numbers or at certain points, then there is no need to try to evaluate this. Okay. And in fact, as x approaches certain numbers, f of x may blow up to negative or positive infinity. And that's going to give rise to a vertical asymptote, right? So we have seen this a few times in the in rational functions. So you may want to think about the domain of the function. Also, it's easy to find f of 0 typically, just because you plug in the number 0, and typically it's easy to find the value of the function at 0. And what's the significance of this? Well, that's going to give you the y-intercept, as long as as long as 0 is in the domain of the function, right? And these are like a very easy first two steps in analyzing functions. Okay. Now, if it's possible, find the zeros of the function, which is to solve for this. Okay, because this will give you all the x values where the function is going to be 0, meaning it's going to give you what? Yeah, it's going to give you the x-intercept or septs. You may have multiple places where the value of the function is 0, and they will help you as you graph functions. All right. You should also find the limits at infinity and negative infinity, because these will give you what? Horizontal asymptotes. As we just talked about this earlier in section 4.6. Okay, are there oblique asymptotes? We talked about vertical and horizontal asymptotes. Oblique asymptotes? There's only one situation where an oblique asymptote could happen, right? And this is that's if you have a function that's a polynomial over a polynomial, and if the degree of p is 1 more than the degree of q. So that's the only situation for oblique asymptotes to exist. And in that case, try to do long division of p divided by q and find the linear function that is as a result of that division. All right, and then you can just do your calculus. All right, so you can find local extrema, that's local maxima and local minima. Try to figure out concavity, concave up or concave down, inflection points, etc. All right, so now look, you have so many tools you can pull out of your toolbox by which or with which to examine a given function f. All right, now again, you know that there are all kinds of functions, algebraic or transcendental, and so we can't do all of them because you can't even list all of the functions, right? So what you can do is first, there are three things. Okay, number one, practice. Number two, practice, and number three, practice. So the more you practice with various types of functions, the better you will be in sketching the graphs of these functions. All right, it also helps once you sketch it, to graph the function using your graphing calculator. But try not to cheat by coming up with your graph using the graphing calculator first, and then try to justify all the points. I mean, that's okay too. Sometimes it is important to do something like that. But I want you to practice graphing, noticing all the details, everything that we talked about. Use these tools to come up with the characteristics of the given function, and try to graph it. And then you look at the, you graph it using your calculator and see if you are right. All right, so the first one, I'm just going to do 2, okay, out of many problems I could do, because I can just keep going on for the next couple of years, but we can't do that. All right, so f of x, this is the first of the 2 questions we will do. before we close 4.6. X minus 1 to the third power and x plus 2. By the way, you don't have to follow every detail of this guideline. Okay, these are just some of the things you may want to look. And you don't have to follow these precisely. Just recognize or try to figure out what you can. And once you think you have enough information, go ahead and try to sketch the graph. Okay, so what do we have here? First, can you tell me what kind of a function this is? It is cubic function multiplied by a linear function. The degree is 4, and it is a polynomial function, right? Polynomial with degree 4, because you have 3 for the first factor and then 1 for the second. So it is a 4th degree polynomial. The leading coefficient is 1. If you multiply everything out here, the first term will be x cubed. This one will give you x, so x cubed times x. The leading coefficient is going to be x to the 4th with 1 as its leading coefficient. And therefore, the end behavior, whatever happens close to the origin doesn't matter. Eventually, as x approaches infinity, f of x approaches infinity. Maybe I should write this down. This, as x approaches infinity or as x approaches negative infinity, in both situations or in both directions, f of x will approach infinity, right? Because as x approaches negative infinity, you have x to the 4th power, which is of course approaching infinity. That's going to outperform or outgrow all the other terms. And the limit at both positive and negative infinity can easily be seen as positive infinity. All right, because it's a polynomial function, the domain of f is all of reals. Okay, it is differentiable everywhere. So the derivative exists everywhere. It's smooth. And what's the word? Nice. Yes. Okay. Do we have vertical asymptotes? No, the vertical asymptotes exist only when you have a gap or a place where the derivative or the function becomes positive or negative infinity. That doesn't happen with a polynomial. So do you understand that with any polynomial function, you will not have vertical asymptotes? Yeah, that's right. Okay. Horizontal, so this is none. Okay. Horizontal asymptote. Okay, that would happen if these numbers, the limit at infinity or negative infinity is a certain finite number, but that's not the case. All right, so that doesn't exist. Oblique asymptote. Remember, the only time this exists is if you have a rational function where the denominator has 1 less degree than the numerator. So this does not happen. So there are no asymptotes. Okay, f of 0. Okay, let's plug in 0 here. It's -1 to the 3rd power, and then 0 plus 2. That looks like -2 to me. Okay, so we have a point on this graph, 0, 2. That's the y-intercept. Okay, now do we know where f of x is equal to 0? Yeah, you can easily find out because the function is already factored. And so that's 0. And that means x is either 1 or -2. Okay, so we have 1, 0. We have -2, 0. And these are the x-intercepts, 2 x-intercepts here. Okay. So look, we have 3 out of infinitely many points. -2, 0, -2. Okay, and then 1, 0, and then -2, 0. Okay, we have 3 points on the graph. Everything else is sort of unknown, except we know that there are no asymptotes. Well, that's encouraging. Okay, well, let's take the derivative, since this is a calculus class. Now, you can multiply all of these out and take the derivative. That's one way to do that. Or since it's a product, let me go ahead and write this again because I want to see this in the same screen. X minus 1 to the 3rd power, x plus 2, right? You can multiply this out and write it as a 4th degree polynomial and then take the derivative. I think I'm going to take the derivative of this product. So it's a derivative of the first which is this times 1 times the second plus the first times the derivative of the second. Looks like I can factor out x minus 1 square. And what's left here is 3 times x plus 2. And over here, I have x minus 1 left. Because I have 3 of these. 2 of these x minus 1s have been taken out. And so you have 1 x minus 1 quantity left in here. So I think I can simplify this. 3x plus 6 minus, or plus x minus 1. And that is x minus 1 square 4x plus 5. Okay. You can set this equal to 0 for critical points. Now, the function is differentiable everywhere, so there is no point where the derivative is equal to 0, but there are places where the there is no place where the derivative is undefined, but you can set this equal to 0 to find all the critical points. So x is either 1 or 1, which is the multiple roots, or negative 5 over 4. Okay, so there are 2 distinct critical points where f prime is equal to 0. At this point, I think I'm going to apply the first derivative test. You can also check and do the second derivative test, but this is basically what's happening. I have an expression for the derivative, x minus 1 squared, 4x plus 5, and those 2 will give me f prime, the sign of f prime. All right, x minus 1, that's, well, x minus 1 squared is always positive unless the inside is 0. So that's positive. This is positive. Now, when x is exactly 1, you have 1 minus 1 squared, and that's 0. But any other x number is going to give you a positive expression, a positive number. 4x plus 5, that's going to be negative here, 0 here, and then any number between negative 5.4 and 1 and beyond is going to give you a positive value, right? Just plug in some numbers and you will see that. All right, so combined, these will give you f prime, and that's negative, 0, positive, 0, positive. Okay. By the way, 1, remember 1 was a 0 or root of multiplicity 2. You have x minus 1, the factor twice. And so that sort of indicates the fact that the sign doesn't change on both sides of 1. It's plus and plus. All right, so graphically, it's going to look like this. It's 0, negative. So the function decreases to this point, and the derivative hits 0 and then increases after that. So the first derivative test applies, right? The derivative of this function goes from negative to positive at this point, negative 5 over 4, and therefore it must be a local minimum. Now at this point, the derivative is 0 and it starts to go up again. Okay, so what's happening here is it's one of those things that, like x cubed, the tangent becomes horizontal just at one point, and it starts to increase again. All right, so this actually, I think, has enough information. I think we can sort of sketch the function if you don't need all the details. Let's see. I think, oops, that makes it a little nicer here. Okay, we have, in the past, we have found 1, 0 is a point on the graph. Okay. We also found 0, negative 2 was on the graph, and then negative 2, 0 was on the graph. So we have 2x. These are the x intercepts, and this is the y-intercept, right? We also found out that negative 5 over 4, what is that? This number is like negative 1.25. It's somewhere around here. Okay. that you have a local minimum. You have a local minimum here. Okay, so this is, I don't know how much lower it gets from -2, but you are going to get -2. And once this is like the bottom part here. This is -5/4. You have this lowest part, or local minimum, and then it starts to increase. Keeps going up. But remember, at 1, you will hit a horizontal tangent. So this will have to go like this, and it continues to go up. So this will slowly go up again. All right. So you can see an inflection point somewhere here. There's an inflection point, maybe 1, and then there's another. Maybe not. Maybe this is an inflection point. Okay, we'll see. And then as you go this way, it'll just keep going up. Now I know it doesn't go down anymore like this, because we have found all local minima. In fact, there's only one local minima, and there's no local maximum. Okay, and we know that because we have checked every critical points. And in fact, there are only 2 critical points, one of which was a local minimum. The other one was not a local minimum or local maximum, right? And so the graph is going to look like this. And if you need additional details, you can. But this is actually a pretty good sketch. There is no vertical asymptotes, no horizontal or oblique asymptotes, and the graph will look like this. This is basically all of the interesting points sketched already. Okay, and if you are interested in concavity, you can find it by taking the derivative of this, which will be a kind of long expression, and then you can find out, where it's concave up and down. I think concavity seems to be up all the way here, up until about this point, and then concavity goes down, and then concavity goes up again. But that's something that you can do on your spare time. Not too hard to do. In fact, as I was talking, I can't stop myself, like, look, I mean, it's so close to finding the second derivative. Why don't we do that? Yeah, nothing else to do. Pursuing a little interesting topic like this, finding the second derivative to find concavity, that's a lot more fun than watching a TV show. Let's take the derivative of this f prime, which is going to give you the second derivative. Okay, the derivative of the first times the second plus the first times the derivative of the second. Okay, applying the product rule, this is what you get. It's 2 4x squared plus 5x minus 4x, right? So it's plus 5x minus 4x plus x minus 5 plus 4x squared minus 2x plus 1. Does it look right? 8x squared plus 2x minus 10 plus 4x squared minus 8x plus 4. 12x squared minus 6x plus 6, no, minus 6. Right, 10, minus 10 plus 4 is minus 6. So you can factor out 12, and it becomes 2x squared minus x minus, oh no, you can't do that. It's 6 I'm talking about. 6 can be factored out. Okay, so that's what you can do to take the second derivative. So if you set this equal to 0, you find the places where the second derivative is equal to 0. Right, so this is 6, 2x, x. I think you can factor this. Minus here and plus here. Yeah, that looks right. Because you have negative 2x plus x. Yeah, all right. So x is either -1/2 or 1, right? And that looks like, these seem like the inflection point to me. You think? I think so, but we can check. I think you can tell, and you can do a sign chart if you like. What I am seeing here is -1/2 is around here. So there's an -1/2. Yeah, there's an inflection point around here. and then 1 is another inflection point, and that seems to be right thing to do, the right place. All right, so to accommodate -1/2 as the place where the concavity changes, so the concavity here is all up, right? And it starts changing. So I think what happens is this is going to go much deeper than that. This is going to go way down, I think, right? So I think what's happening is that this is going to go way down like this, and then it still is going to be it's going to come up very quickly up here, and then the concavity changes right here at -1/2, and right here, and it starts to go up. I mean, so the concavity is down here and down until this point, and from here on, the concavity is up again, going up like this. So the inflection point happens to be right here, and where x is equal to 1/2, -1/2. That looks like an inflection point, right? So that seems to be the right kind of equation or the graph for this function. All right, let's do one more, and if you will, I will do. Let's see, I'll do a rational function, and then we'll just call it quits, even though we can continue to do more and more of this. All right, so let's do the last question. Okay, here's the last question. X squared over x minus 1. All right, let's sit back and look at this and carry on a little conversation with your friends. First, what kind of a function is this? Well, it's a polynomial over a polynomial. Hopefully you agree that this is a rational function. The degree of the top is 2, the degree of the bottom is 1. Okay, so the degree of the top is exactly 1 more than the degree of the bottom. Okay, so this tells you that you probably should do what? Long division, right? Let's do long division, x squared divided by x minus 1. Because, I mean, you can see that this is going to give you a line, which is an asymptote, and that means you have an oblique asymptote. And then we have maybe something else going on. By the way, f is not defined at x is equal to 1, right? And in fact, you could see that there's a vertical asymptote there when x is equal to 1, because when x is close to 1, this function blows up either to negative or positive infinity, depending on which way you approach it. But let's go ahead and divide x squared by x minus 1. You have x, so x squared minus x, and then subtracting, you will see x. You can still divide, okay, plus 1, x minus 1, and the remainder is 1. So this tells you f of x is actually x plus 1, that's the quotient, plus 1 divided by x minus 1. Okay, so what can we say? This is the vertical asymptote, the oblique asymptote is y is equal to x plus 1. Okay, this becomes a very important piece of information here, right? And then this approaches 0 as x approaches infinity, of course, right? And so that means the graph gets closer and closer to the line x plus 1. Also, can you figure out what f of 0 is? Yeah, I think that's easy to find out. That's 0, because it's 0 squared over -1, right? And in fact, so this is the y-intercept. In fact, this is also the x-intercept, right? Because if f of x is equal to 0, that means x squared over x minus 1 must be equal to 0, and therefore x has to be 0. So this means 0, 0 is the x-intercept, the only x-intercept, and of course the only y-intercept. That's the only place where the graph crosses or touches the axis, the x or y axis. All right, so you do know a lot already about this function. Well, let's take the derivative of this function. All right, so it's going to be, I like to take care of the denominator first. You square the denominator, and then the top. So what is the numerator in the quotient rule? It's going to be the derivative of the top minus times the bottom minus the top times the derivative of the bottom. I always say those things as I do this. Okay, so this is going to be 2x squared minus 2x minus x squared, and that's x squared minus 2x divided by x minus 1 squared. Let's rewrite this. The derivative of this function is x times, I'm factoring out x minus 2, all over x minus 1 squared. Okay, so x can't be 1 because if x is 1, this is not defined. And in fact, f itself wasn't defined. And so you know that this is equal to 0 at x is equal to either this or that. So that's x is equal to 0 or 2. And these are the only critical points on here. Okay, so now we have a very nice expression. Let me go ahead and erase this. Nice expression for a for the derivative. So I would like to do the sign chart. Okay, so you have x and then x minus 2 and x minus 1 squared. And after these 3 rows, we can analyze the sign of x prime. So x is negative, of course, when x is negative. X is 0 when x is 0. When it's silly to say that, right? X is positive when x is positive. So this is the sign, the line of the signs for x. X minus 2 goes negative, and when x is 0, it's still negative. X is still negative here. Once x reaches 2, 2 minus 2 is 0, and after that, it will be positive. X minus 1. Quantity square. Oh, I forgot that, huh? So I should say f prime is undefined at x is equal to 1. So actually, we have three critical points. Okay, so I am sorry about that. I need to do this over again because I really have to include all of the critical points. Okay, so the critical points are 0, 1, and 2. Okay, x is negative here, 0, positive, 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 positive. X minus 2 is negative, 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 0, positive. Okay, x minus 1 squared, that's going to be positive everywhere except when x minus 1 is 0, which is happening right here. Otherwise, it's always positive because you square the quantity. And once you have these 3 lines, you can see this is positive 0, this is right here, 0. And then you have negative, and then 0, negative again, 0, and positive. So what does the graph look like? It's going to go up, 0, down, 0. This is not the negative sign. I'm just saying there's a horizontal, tangent, and then horizontal tangent, and then goes down again, and 0, and goes up again, right? So the graph roughly is going to look like this, or does it? Okay. I made a mistake here too. See, this is in the denominator. We never had this before. Sorry about that. If this is the denominator, 0 denominator is not going to give you 0. Okay, and in fact, this is undefined at this point because x minus 1 squared happens in the denominator. So there's a little hole. We don't know what's going to happen at this point. Okay, so that's what's happening with this. And that's helpful because now we are ready to graph this, right? what does this function look like? X squared over x minus 1. I will try to graph it over here. Let's go ahead and use this color for the axis. I think that would be good. All right, so I know I have a vertical asymptote somewhere, right? And in fact, I said the vertical asymptote happens when the denominator is 1. Because that's when, oops, okay. That's when the function blows to positive or negative infinity. So let's go ahead and mark that. When x is equal to 1, you have a vertical asymptote. And I am going to go ahead and write that. So vertical asymptote, x is equal to 1. All right, I do have this 0 here. And I also have what? Oblique asymptote, x plus 1. Let's go ahead and graph that. Maybe we can use a different color for this. Yeah, all right, x plus 1 is, y is x plus 1. So the y-intercept is 1, the slope is 1. The graph is going to be like this, okay? And let's go ahead and write that. Oblique asymptote, y is equal to x plus 1. Okay, we also have 0, 0 as a point on this graph. Okay, and in fact, that's the only point where the graph crosses x or the y-axis. We have established that here. All right, and then we have this sign chart, which tells you, by the way, the sign chart says this is a, so f has a local maximum at 0. The point I just charted, or I plotted, happens to be an absolute maximum. Okay, and so it's really easy to graph the rest of this to the at least on the left-hand side of the vertical asymptote, because we have this point, and the graph has to approach the oblique asymptote, and this is the maximum point, so it has to go this way. Okay, and because it's a maximum point, it has to start to go down, and it has to approach the vertical asymptote. So you really don't have any choice but to draw that. Okay, where this gets closer and closer to the vertical asymptote, this one gets closer and closer to the oblique asymptote. All right. On the other hand, and by the way, that is, we have just drawn this part here like this. All right, and now this point here, f has a local minimum at 2, right? So, and at this point, maybe you want to find out f of 2. Okay, what is f of 2? It's 2 squared over 2 minus 1, and that's 4. So 2, 4 seems to be a, what did I say? Local minimum. 2, 1, 2, 3, 4. That's the local minimum. Okay, and again, since we know it's a local minimum, and there are no other, local maxima or minima except for 0, 0, and 2, 4. So if this is a local minimum, it has to get closer and closer to the oblique asymptote. You don't have any choice but to go this. And it can't go under like this because it was a local minimum. So it has to move up from here and gets closer and closer to the vertical asymptote. So that must be the graph of this function. All right, so that is our function x squared over x minus 1. You see, it was time consuming, okay, but really every part of this that you do by hand requires a lot of thinking, a lot of synthesizing your knowledge and tools that are now in your toolbox. Okay, so this is an excellent exercise. It forces you, graphing a function like this will force you to be able to recognize these important features and the tools that you have so that you are aware of what you can do as you analyze these functions. Okay, so do your exercises and master the skill of graph sketching.